So here's the property. You guys ready? Remember how we talked about attention spans? If you're dividing two radicals that have the same index, like a square root divided by a square root, you can change that into a single root and simplify the fraction that's left over. Sometimes that's helpful. Sometimes it's not. Sometimes it is. So go back to page 241 in your book. And take a look at the problem 4 got it problem.
Four got it. I forgot it.
There's a problem 4 got it problem, right?
Wait, does no one get it? Four got it.
This one here?
Yeah.
So let's use this property here. We're dividing a square root by another square root, right? So we can turn that, according to this property, into one big giant root, and then we can simplify the fraction that's left over. So we can change this into one square root of a single fraction, 50x to the 6 over 2x to the 4. A lot of times this helps. Sometimes it doesn't really help. This time it does help a lot. 50 divided by 2 is 25. And then x to the 6 divided by x to the 4 is x squared. Don't worry about it right now. We'll get it back in a second. X to the 6th divided by x to the 4th. When you're dividing, you subtract exponents. 6 minus 4 is 2. Okay, square root of 25 is 5, and the square root of x squared is x. 2 divided by 2 is 1, so it's x to the first power. So same page, let's take a look at problem 7 right here. Same page, problem 7. It's a similar type of situation. First thing you got to check is, are you dividing by the same kind of root? We have a square root divided by a square root. So yeah, they're the same type of root. Yeah. So let's change this into one big square root and see what happens if we can simplify the fraction. So we have 48 x to the 3rd over 3x y squared. This one's a little different. Not everything simplifies so nicely. 48 divided by 3 is 16. Yeah. And then we have this x to the 3rd divided by x to the 1. X to the 3rd divided by x to the 1. You subtract exponents. Remember, 3 minus 1 is x squared. But then we have this y squared on the bottom that does not simplify with anything on top. So that y squared just stays y squared on the bottom of a fraction. Alright? But the 16 x squared can move up to the top. So that's all the simplifying does for us right there. We don't completely get rid of the fraction. We end up with a more simple form of the fraction.
So you just cross off 1 over 1 x.
48 divided by 3 is 16.
3 divided by 3.
And then 3 minus 1 is x squared.
Yeah, but don't you just like cross off the x? No.
So this one x down here crossed off with one of these up here. That's why there's x squared on the top.
Yeah.
We good? Alright. But we're still left with a fraction here. We didn't get completely rid of that fraction. So what you're going to have to do is use that same property we just learned, but in reverse. Now we got to separate this back into two separate square roots. So we combined it into one root to simplify the fraction. Now that we simplify the fraction, split it back up into two square roots and simplify each root on its own. What's the square root of 16x squared?
Can I have Judah Whitmore to attendance for checkout, please?
Yep. And the square root of y squared? So it's 4x over y. Okay? So going back through this, you guys, we took these two square roots and made one square root. What was the purpose of that? To simplify the fraction, right? So we still ended up with a more simplified form of the fractions. We had to split that back up into two roots, and then you simplify the two roots individually. And we ended up with 4x over y. All right? Now, question number 8 adds something else that we need to talk about. Same page, write down problem number 8. So we can start this one the same way. We combine this into one big root and simplify as much as we can. 20 divided by 45. It doesn't divide evenly, but at least simplify it. Simplify the fraction like you learn how to do in elementary. Come on, you guys. 20 over 45. 4 over 9. There we go. And then one of these a's up top cancels with one of these a's on the bottom.
A on the bottom.
So we have a single a on the bottom of the fraction. And then we have this b that cancels with one of these b's down here. So it's going to be b squared. Does this b to the 1 cancel with that? You with me so far? But now we still have a fraction here, so you're going to want to separate this back into separate square roots and then simplify each root. Square root 4 is 2. But this one has a bit of a problem. 9 comes out as a 3, right? And the b squared comes out as just a b. But then you have that square root of a left over. No, unfortunately.
You have to bring them back to the top.
You guys understand where we at least got to here? We good up until this point? Where'd the 3 come from? Square root of 9. Where'd the b come from here? Square root of b squared is just b. But then the a was left over on the inside, so you have to leave it as square root of a. Okay? You guys need to write this phrase down and put a box around it. This is something that, and it's not your guys' fault, this is new Common Core crap, but this should have been taught back in elementary school. No, junior high school is when they should have been taught. You cannot leave a radical in the denominator. By radical, I mean some kind of a root, like a square root or a cube root. Any kind of root, that's called a radical. You cannot leave a radical in the denominator. So even though this answer isn't incorrect, it's not in the right form. We didn't do anything wrong, but isn't this square root of a, doesn't that count as a radical in the denominator? You can't leave it there. Okay? It's not considered fully simplified. So before I show you how to deal with it, let's take a look at a more simple problem here. Write this problem down. 2 over the square root of 5. 2 over the square root of 5. That's also a problem, right? Isn't there a radical in the denominator? Now here's where this actually all came about. It's kind of stupid, if you ask me.
Oh, it's just the square root of 1.
Not quite. You guys do realize that these calculators haven't been around forever, right? Even as early as, I don't know, 25, 30 years ago, they didn't have calculators like we have them now. So they had to do a lot of this stuff either by hand or on slide rulers, just different things. This problem right here would have been very difficult to do by hand or even with a slide ruler. So they came up with this rule that you can't have a square root in the bottom of a fraction. It really doesn't matter nowadays, because if you use your calculator and type in 2 divided by the square root of 5, there's absolutely no problem with it. It's 0.89. Okay? So today's modern calculators can deal with it. They just couldn't do this problem by hand very easily before these calculators. So they came up with this rule that for some reason we're still following. Don't ask me. But
That's not what you guys saying.
it's because I didn't get a say in the matter. So here's how you simplify it. We need to come up with a different form of 2 over the square root of 5 that's numerically equivalent, just doesn't have a square root in the bottom. Here's what I mean by numerically equivalent. If I took 2/3 and multiplied it by 4 over 4, what do we get? But isn't 8/12 numerically equivalent to 2/3? Why is it the exact same numerical value? All we multiplied it by is 1. Okay, 4 over 4, which is 1. What if I had taken 2/3 and squared the top and squared the bottom? What would I have ended up with? 4/9. Is 4/9 numerically equivalent to 2/3?
No.
They're not the same decimal. 4/9 is not the same as 2/3. What I'm getting at is you can't square the top and bottom of a fraction and end up with the exact same ratio. Because what a lot of students come up with is, well, let's just square the top and bottom to get rid of that square root. It gets rid of the square root, but you end up with a completely different fraction that's not the same ratio. You guys see where I'm going with this?
Yeah.
So the only thing we can do to this fraction right here is multiply it by something over itself. Okay? Like, I could multiply it by 3 over 3 or 10 over 10. We got to be clever about this, though. If we multiply it by the square root of 5 over the square root of 5, for example. What is the square root of 5 divided by the square root of 5?
0 or 1.
It's just 1. So am I changing the original fraction? No. But what's square root of 5 in particular? What is the square root of 5 times another square root of 5?
25. Square root of 25.
It's the square root of 25, which is? So there's no more square root in the bottom. Okay. 2 times the square root of 5 is just 2 times the square root of 5. So this is the version that they were looking for, 2 root 5 over 5. Okay. Now if you check it on your calculator, 2 divided by root 5 is 0.89. If you type in 2 times the square root of 5 divided by 5, you get 0.89. So it's the exact same ratio, it's just a different form of the answer. You guys with me? So this process, even though it's kind of outdated and we don't really need to do it anymore, we still do it. It's called rationalizing. Rationalizing the denominator. You need to write this down. rationalizing the denominator. All it really means is you get rid of roots in the bottom of a fraction. And it doesn't apply just to square roots, it's any type of root. So just for quick practice, write this problem down here. 3 over the square root of 7. That would not be an acceptable answer on your homework or on the test if you left it like that, even though it's not incorrect technically. What would you have to do to this one? Multiply it by, say it louder, square root of 7 over square root of 7. So then you end up with just a 7 on the bottom, because the square root of 7 times the square root of 7 is the square root of 49, which is 7. And then on the top, 3 square roots of 7. Okay. What if we had 2 divided by the square root of x? You do the same thing. You multiply it by square root of x over the square root of x. So you have 2 square roots of x over x. So let's go back to the problem we were just working on. Where, didn't we have like a square root of a in the bottom?
Yeah.
So, what are we going to do with it then? Multiply it by square root of a over square root of a. So then in the numerator, you're going to have 2 square roots of a nothing's really happened to the 3 and the b. That's just going to stay 3b. And then the square root of a times the square root of a is the square root of a squared. And the square root of a squared is a. So that would be the version of the answer that they're looking for. 2 square roots of a over 3ba or 3ab if you want to do alphabetical order. Okay, you with me so far? So we need some more practice. Oh yeah, we do. Somewhere we're supposed to have more practice. Here it is. So number 9 and 10. Those are on the same page, right?
No, 242.
All right, 242 then.
Number 9's not too bad. Square root of 3xy squared over the square root of 5xy cubed.
What should we do first? Most of the time, writing it as one big fraction will help you simplify a few things. So take it into one root instead of 2 separate square roots. Nothing happens with the 3 and the 5. The x's are gone. And then y squared over y cubed just means there's a single y. Yep, there's a single y on the bottom. Now that's as far as a fraction simplifies. So I would separate this back into 2 square roots again, square root of 3 over square root of 5y. And that's as far as the simplifying goes. So the last part of this is just rationalizing. It is not okay to leave this square root on the bottom. Remember, we can't just square the top and bottom of a fraction. That doesn't work. You end up with a completely different ratio. And the square root of 3 isn't the problem. It's the square root of 5y. That's the problem. So you multiply it by itself. The one that's the problem is the square root of 5y over the square root of 5y. So yeah, on the bottom we're just going to have a 5y. If you multiply a square root with itself, the square just disappears. And you're left with what's on the inside. So it's 5y. But square root of 3 times square root of 5y is the square root of 15y. Now how about this? You guys tell me yes or no. We might not be finished. What about this? This y cancels with that y. Is that alright? You sure? Y divided by y, shouldn't they cancel? One's underneath the root. That's no good. So that doesn't work. What about the 15 divided by 5? Can we make that turn into a 3? Same thing. 15 is underneath the root. This is as far as this problem goes. Okay. Let's take a look at problem 10. That's the final answer on that one. Yep. Square root? Correct. What do you think? Combine this into one cube root and see what simplifies? Might not be a bad idea. Well, let's start with 12 over 10. That's pretty easy. 12 over 10 is 6 over 5. And we're going to have an a squared. Is it going to be on the top or on the bottom? A squared on the bottom. It can be a b squared on top. And a c on the top. That's as far as the fraction will simplify. So at this point, you're going to want to separate it back into two cube roots. One on the top, and another one on the bottom. So it's the cube root of 6b squared c over the cube root of 5a squared. Now I need you guys to really watch closely on this one. We were supposed to do this problem. 5 got it first. Wasn't there a problem 5 got it before numbers 8 and 9? Or 9 and 10?
Yeah.
Oh, we were supposed to do that first.
Missed it.
Shoot.
Oh no, we're sinners.
Well,
Pumpkins.
let's take a look. Well, just look up here. You don't need to write it down. No, we got to do this one first, or this other one's not going to make sense. Okay, seriously, you guys don't need to write this down. I just want you to watch it, though. And this, you want to write it down. You remember how I said most of the time it helps to combine it into one cube root or one square root? Would that even help on this problem, though, if we combined it into one cube root?
No.
Does anything simplify at all?
So don't go through the trouble of combining it. Nothing would simplify.
Now, here's the thing, though. We can't have a cube root on the bottom of this fraction. If we just multiplied it by a cube root of 5y squared, isn't that what we do with square roots? You multiply by itself?
You guys listening carefully? All your distractions are put away. 5 times 5 is 25. Does 25 have a cube root? And then y squared times another y squared is y to the 4th. Is 4 divisible by 3? So multiplying it by another cube root didn't help because we're still going to end up with a cube root. You guys understand what I just said? Multiplying by itself works with square root.
Wonderful.
What if we did another cube root of 5y squared?
Oh gosh.
Why would we do that?
What's 5 times 5 times 5? 125. And 125, what's so special about 125?
That's a cube.
It's a perfect cube. What about y squared times y squared times y squared?
Why?
6 is divisible by 3. And what is 6 divided by 3? So you're going to have the y squared, and what's the cube root of 125? 5. So all 3 of these cube roots down here on the bottom multiplied together, what's that going to result in? 5y squared. Here's what you guys need to remember. If it's a cube root, how many of them does it take in order for the cube root to disappear? 3. Because this is a cube root. It takes 3 of them. Why did it only take 2 for a square root? Because the index is 2. Here the index is 3. It took 3. You guys see the difference here? Okay. So the cube root of 5y squared multiplied with itself
3 times results in just 5y squared. We good? But you notice in the numerator these are not all exactly the same, so the cube root's not just going to disappear. You have to multiply the terms on the inside. 7 times 5 times 5 is 175. X y to the 4th. Okay. Now, anytime you have an exponent that's higher than the root, that means you're not fully simplified. I mean, this 4, isn't that bigger than 3? So we got to simplify that. How many times does 3 go into 4? So there's going to be a y to the 1st power. 175, it's not a perfect cube, and there aren't any factors either of 175. So it stays as 175. What about the x? Just stays as an x. Now this y to the 1st is because 3 goes into 4 one time, but isn't there a remainder?
Yeah.
So there's a y to the 1 on the inside. Over 5y squared. No! Can't this y right here cancel with one of these y's right here?
No.
This y right here?
Yeah.
And this y right here?
Yes. Yes.
Yeah, they're both outside of a root. Okay, so this y cancels with one of these y's on the bottom. So the final answer is the square root of 175xy. Sorry, the cube root, not the square root. The cube root of 175xy all over 5y. So let's go back, let's go back to the problem we were trying to work on before this one. Because right now we have a cube root of 5a squared on the bottom of this fraction. What do we multiply by to get rid of the cube root of 5a squared? Just the cube root of 5a squared? You got to go twice. Top and bottom. So if you have the cube root of 5a squared multiplied by itself 3 times, it's just 5a squared. But then in the numerator, we have 6 times 5 is 1/3 times 5 is 150. A to the 4th, b squared, c. Now you've got to run through in your head for a second here. 150. It's not a perfect cube by itself, but you got to think if anything multiplies to 150 that's a perfect cube. There's 8, there's 27, there's 64, there's 125. Any of those multiply to 150. I don't expect you to know it off the top of your head, but you ought to get out a calculator and just double check. 150 divided by 8, does that work? What about 150 divided by 27? 150 divided by 64. You always ought to double check just to make sure. So what does that mean about 150? It just stays as 150. Now this exponent of 4 is larger than the type of root, so we got to simplify. How many times does 3 go into 4? So that means we have an a to the first, and then what's the remainder? So a to the first on the inside. And then we have a b squared times c all over 5a squared.
And you reduce it with 1b squared.
And then we simplify one more time. This a out here cancels with one of these a's down on the bottom. So final dang form of this answer is a cube root of 150 a b squared c all over 5a. Okay, you guys, I need you to listen to me very carefully. This way that I've just showed you, I think, might be the easiest to understand, but it's not necessarily the easiest way to do this problem. Okay? Let me show you problem 5 got it one more time. This way is a little bit harder to get at the beginning, but if you can understand this, it's so much faster. So if you're not interested in learning a new way, this way works that I've shown you, it just takes a little bit longer. So this is the problem 5 got it problem, right? Isn't this the problem 5 got it problem? Here's a different way to do the same problem. It is quicker, but you got to watch carefully. If you're just watching halfway, you get it mixed up with some other kind of method. Is 5 a perfect cube? No, it's not. Here are the perfect cubes. 8, 27, 64, 125. Are any of these numbers here a multiple of 5? So what do I need to multiply 5 by to make it equal 125? 25, right? So I'm going to multiply this by a 25 right there. Because what is 5 times 25?
125. Now the other problem is the variable. Y squared. 2 is not divisible by 3, is it? How many more y's does it really need to be divisible by 3?
Just needs one more y. So multiply it by that. And all you need is one cube root. Now you don't have to multiply it 3 times. You just need to really multiply it by the missing pieces it needs to be a perfect cube. It needed a 25 and it needed a y. What is 25 times 5 right here? And what's the cube root of 125? 5. And then y squared times y is y cubed. But what's the cube root of y cubed? Cube root of y cubed?
Y.
is just y. So all you have on the bottom is 5y. And on the top, 7 times 25 is 175. And there's no simplifying we have to do. Compare, isn't it the same answer? So if we go back, sorry, one more. If we took this right here before we multiplied it by 3 different cube roots. So we have cube root of 6b squared c over the cube root we're just redoing this problem one more time to show you a quicker way. Originally we just multiplied it by 2 more cube roots of 5a squared. That works, but it is a little bit of a longer way. Really, what does 5 need to become? 5 needs to become 125, because 125 is a perfect cube. So what does it need to be multiplied by? A squared is too small, because 2 is not divisible by 3. So it just needs another a. So then all we would have left on the bottom of this is 5a. And on the top, if you have 6 times 25, is 150. Times a b squared c. Same answer, quite a few less steps. Okay. So consider this problem then. Hurry up, write this down. The cube root of 6x over the cube root of, well, sorry, yeah, we can do it. If we combine this, first of all, a few of the things simplify. 6 over 3 becomes a 2, but then we have x and a y on the bottom. So then we have the cube root of 2x over the cube root of y. So rather than multiplying this by 2 more cube roots of y, how many more y's does this need so that we can cube root it? It needs 2 more, so just multiply it by the cube root of y squared. Hold on. Cube root of y times the cube root of y squared is the cube root of y cubed, which is y, and then over here we have the cube root of 2x y squared.
Okay, that was a lot more sense.